Hello, and welcome back to Compressible Flow. I'm Professor Steve Miller. Today, we'll be talking about shock expansion theory, which of course is the combination of our shockwave theory, which we previously developed, and our newly developed theory of expansion waves of Prandtl-Meyer. We'll then immediately apply the shock expansion theory derivation to the diamond airfoil problems. These are simple airfoils to illustrate the most important concepts of supersonic flow, where systems of shock waves and expansions occur. Then we'll talk about the all-important idea of wave drag, which dominates drag at high speeds. And then we'll do an asymptotic analysis for the turning angle going to infinity of the Prandtl-Meyer expansion waves to find the so-called maximum expansion of the flow. Let's get started with these important concepts. Let's start with a quote. This one reads, "Mythologists and experimental theologians are needed for the development of a new method of attack." This was written to none other than Theodore Meyer while he was in the trenches after recovery in World War I. This was addressed to him and mistranslated from the telegram, "Meteorologists and experimental physicists." This, of course, was a telegram sent to him requesting that he report from the trenches of World War I to meet with Fritz Haber. He is indeed the father of German warfare chlorine gas attacks. And of course, Meyer was recruited from these trenches to go work on this problem. I believe this is likely the reason he left research altogether to become a school teacher after witnessing and, of course, unfortunately, having to help by force the development of so-called chemical weapons in use in World War I. Let's now look at shock expansion theory. Indeed, it's the combination of shocks and expansions for the calculation of particular aerodynamic forces. So now in this class, we're going to take our oblique shockwave theories, which we previously developed, and our newly developed tool of expansion waves of Prandtl-Meyer and apply them to particular problems to find the variation of static pressure acting on a vehicle as it moves through the air to estimate lift and drag. And we'll show this through one particular example and example problems, but you can apply this to anything, of course. This analysis typically involves two-dimensional sections such as airfoils. Of course, this all can be done in 3 dimensions. Our example here has a unit span, meaning, say, 1 meter into the page off the 2 dimensions in the z direction. Now, more complicated analysis will, of course, involve 3 dimensions, but there's nothing in our theory that's really 2-dimensional anyway. We're just applying it to, say, shocks from wedges, which are 2D and planar. We can, of course, use the conic sections and apply the same Prandtl-Meyer expansion theory in 3 dimensions. Let's get started. First, we'll introduce the diamond airfoil, and we'll do this through one example from computational fluid dynamics, as shown in the particular figure on 307. Here I write CFD solutions for a diamond-shaped airfoil at 2 angles of attack, for a Mach number greater than 0, of course. Here, the flow is supersonic in both cases. The airfoil is actually a diamond shape, so the airfoil, in 2 cases, left and right, is shown as the white diamond. The airflow moves from left to right. On the left, it has a supersonic flow Mach number, which creates an attached oblique shock wave at the leading edge of the airfoil. And then the flow is turned around the airfoil and it expands and is turned back and reattaches to the airfoil through this expansion wave. So these are expansion waves above and below the airfoil. And the flow goes to a final oblique shock wave because, of course, the flow is turned once again to be parallel with the original direction in this particular case. Here, the angle of attack is 0 degrees, and indeed, you can see the flow is symmetric about the centerline axis or chord of the airfoil. Let's take the exact same supersonic Mach number and allow it to go over the airfoil, but now we angle the airfoil at none other than 5 degrees. So alpha, the angle of attack, is now 5 degrees with respect to the incoming flow. You'll now immediately notice that we have indeed almost exactly the same flow pattern, but it's no longer symmetric about the chord. This is, of course, because the flow going over the top of the airfoil, which is traditionally the suction side, has a oblique shock wave, which is having a different wave angle relative to the incoming flow direction. Why is that? Well, of course, indeed, it is because the flow turning angle is smaller than, of course, the flow going over the bottom of the vehicle. This also results in 2 different corresponding oblique shock wave angles, beta, which you see. Once again, there's an expansion around the top and bottom parts of the vehicle, and there's again a trailing oblique shock waves. In fact, if we increase the angle of attack even more, we would eventually obtain an expansion above the vehicle on the pressure side of the airfoil, and retain the oblique shock wave on the bottom side of the airfoil. So remember, you'll have shocks where the flow turns into itself, and expansions where the flows turn out of itself. The flow moves from left to right, and of course, the streamlines are discontinuous on the shock fronts and continuous everywhere else in the flow. It's very much true also that you can see the flow is everywhere supersonic in these cases. For example, we do not have detached shocks, so there's no reason to expect we have subsonic flow in these particular flows, unless, of course, the Mach number is in the transonic regime. Let's try and analyze these particular cases with our newfound tools and also make some notes about them in the following slide. Let's do that now. Here's the graphic illustration of the problem I just showed. So in figure 308, we have an incoming Mach number, M1 greater than 1, and we'll call this state 1 in front of the vehicle. It's a marching problem. We'll march downstream from left to right. Now the vehicle, the diamond airfoil in this case, has a chord which goes from the tip to the trailing edge, and a thickness, which is the maximum distance in this cross-stream direction of the body. In this case, it's from the two tips of the triangles, respectively. It also has a small half angle epsilon. The total angle of the leading wedge, if you will, is, say, 2 epsilon. We would call the half angle epsilon, because of course it's half the total angle of the nose cone of the vehicle, in this case the diamond airfoil. Since this particular case is symmetric, we would label the upper parts of the flow 1, 2, and 3, and maybe 4 after the last trailing shock. The bottom parts of the 4 might be, say, 5, 6, and 7. But of course, 2 would be equal to the 5, and 3 would be equal to the 6, because we have a symmetric flow. And so we only have to calculate the flow over the top of the airfoil. As long as the airfoil is symmetric, the flow is steady, and we are at a 0 angle of attack. That is, the angle of attack here is measured from the chord angle with the incoming flow angle, and that value should be 0. Of course, there's an ambient pressure, P sub infinity, and as we go from state 1 to 2, we would obtain a new static pressure which is higher than, say, P1. That would be P2. Over the expansion, the pressure would decrease and we would find P3. Note that the static pressure, P2 and P3, acts over the whole surface of the airfoil, of course, everywhere, but it's just the internal stress of the fluid. This also occurs in region 3. Notice these, say, force vectors from the pressure acting normal on the airfoil itself have different lengths. So, of course, P2 is much higher than P3 because the expansion has lowered the pressure, and P2 is greater than P1. It remains to be seen, depending on the angles of the flow from 2 to 3, if 3 is larger than 1 or less than 1. It will depend on the strengths of the shocks and expansions, respectively. Nonetheless, let's try and continue and analyze the problem where there's particular sides A, B, C, and D, where each side is length L for a symmetric diamond airfoil, which is symmetric about, say, its cross-stream direction at maximum thickness and the axis where there's a second plane of symmetry. Let's try that and make a few notes about the situation. So you see, this is symmetric in geometry, but only in specific cases. If we have non-zero angle of attack, then of course the flow is not symmetric about x, as we showed in the contours plotted from this particular CFD solution. Now, you'll note that the flow is initially deflected by an angle epsilon and therefore compressed by the leading oblique shock waves. The flow expands at mid-chord, that's C over 2, by an angle 2 epsilon. So you see from 1 to 2, the flow is turned in itself by a flow turning angle of epsilon, and the flow is now moving parallel to wall A. And if it went forward with no expansion, it would just continue on. To turn the flow back to the original direction, we would have to go through a turning angle of epsilon, and to turn the flow through the full expansion, so it's parallel with wall B from, of course, region 2 to 3, we would have to go through an angle 2 epsilon. And this is what I noted, of course, in this fourth bullet of page 810 of the slide deck. Now at the trailing edge, something else has to happen. Once again, the angle of the flow from 3 to, say, 4 has to be turned again. Why? Because the flow must be symmetric. And so we know, because it's steady and the airfoil is symmetric, that we know that the streamlines must be parallel in the particular wake. at least on a time average basis. And so the flow turns through another turning angle epsilon, and indeed an oblique shock wave must form at the trailing edge of the vehicle. This also balances out the pressure, and we would not expect to have any slip line here. With particular angles of attack, you might imagine that through these different systems of shocks, we might actually have a shear layer or slip line behind the vehicle in the wake, where we would have unequal entropy and, of course, equal static pressures and other values being unequal, including velocities. Naturally, the velocity direction would also be equal, so we can conserve our conservation of mass equation. Now, only forces on this particular symmetric airfoil is drag, and the lift is canceled out because it's symmetric. If we have a non-zero angle of attack on this symmetric body, like this airfoil, then of course we would have lift. So we would not expect lift to be created on the body, as the pressures in the y direction or cross-stream direction canceled out from sides A to C and B to D respectively. If we, of course, have an angle of attack, the pressures would be unequal in the top and bottom respectively, even though they act on relatively the same areas, but in different directions. And again, we would have drag and lift. This is very interesting. We would combine our theories, of course, shock waves and expansions, to solve these particular problems, which we'll do soon. Now, we can easily write the so-called drag of the diamond airfoil by integrating the pressures through the shocks and expansions on faces A, B, C, and D of the diamond airfoil. The pressures, the static pressures acting on the surfaces, are dominated by the shocks and expansions. That's because the shocks raise the pressure so much, and they have such a tremendous effect on the flow relative to other effects. In fact, they're the dominant mechanism and physics within the flow. Therefore, the pressures on the vehicle and their integration rise tremendously as the shock waves form on the vehicle. This is indeed the rise of the wave drag. So the wave drag can be approximated with equation 546 in the particular equation shown on the page. You'll see the wave drag goes as the integral along the surface of the pressure with respect to every differential element S in the outward pointing direction. And so we can just integrate pressure with area to find the drag. Now, for symmetric diamond airfoils, we know the lift is 0, so we're not even going to bother integrating it and showing it. But we can concisely write the drag, that is the wave drag on the symmetric diamond airfoil with 0 angle of attack, as in equation 547. We'll write the wave drag goes as the pressure on 2 times its length times sine epsilon, which will project the pressure and as a force over the area in the x direction, the streamwise direction, minus the pressure in 3 times the length times the sine epsilon, which projects it, of course, in the opposite direction. We can then simplify and move out sine epsilon and write 2p2 minus p3 times the thickness over 2. So, of course, we're writing L sine epsilon as the thickness over 2. You can see this operation through trigonometry of the figure in 308 of the slide deck. Take a second and do that. Now, indeed, once we've done that, you can see that 2 over 2 cancels, and we're left with an approximation of the wave drag as P2 minus P3 times the thickness. So you can see as the thickness goes to 0, the drag will go to 0, as the airfoil becomes thin, and the pressure from the shock minus the pressure from the expansion is proportional to the drag. Of course, the shock pressure is tremendous. For high-speed flows, you might as well just approximate P2 as the wave drag if you're doing an approximation. You can also see the drag due to the wave drag goes exactly as the thickness. It's really a linear type operation if you hold pressures constant, which is a little bit naive, because of course the pressures will change with changing thickness because that changes angles and everything. This is, of course, much more complicated for non-zero angle of attack, because you'd also have to calculate lift, and you won't have nice cancellations in 547. Naturally, your homework problems show these types of solutions to be found. Let's continue and discuss the idea of D'Alembert paradox. In previous classes, you learned the D'Alembert paradox applies to the idea of inviscid, incompressible flows over bodies where indeed there's no drag. There's no drag in those types of flows. Now, if we have compressibility and high-speed flows, of course, shock waves appear. So supersonic flow, with the existence of so-called wave drag, which we just introduced, will indeed alter the most traditional theories of aerodynamics, and of course, help us alleviate the strange D'Alembert paradox. Remember, for example, D'Alembert paradox will state that, indeed, quote, drag is zero for inviscid flow over an airfoil, a finite span at subsonic speed, end quote. Of course, this was found mathematically by D'Alembert and written in his famous treatise. And it was, of course, proven mathematically. But of course, all objects actually do have drag, especially in viscous fluids, because of course they would slow down due to the aerodynamic forces. But mathematically, that did not agree with the present theory at the time. Of course, D'Alembert was aware of these assumptions of the mathematical theory. He wasn't naive or stupid in any matter of fact. In fact, D'Alembert can indeed be credited with creating the first partial differential equations in mathematics, which is indeed the way we write all physical laws of the world we live in mathematical physics. Now, this theory, which we just used in D'Alembert's paradox, made the assumption of incompressible flow. Here we made no such assumption, and say a finite span airfoil at higher speeds will have these discontinuities, and indeed we do find a drag, which is the wave drag. And so in some way we have resolved D'Alembert's paradox by including the effect of compressibility and the theories of Prandtl-Meyer student Theodore Meyer. Let's take a second and appreciate one of my absolute favorite persons who ever existed. And there's amazing biographies you can buy on him. Here, Jean-Baptiste Laurent D'Alembert. He was born in November 1717 and lived through 1783, and he was French. He wrote many interesting treatises, and one quote I prefer from him is that time destroyed all models which the ancients may have left us in this genre. And that is because the mathematical enlightenment in France in the 1700s was humongous, with the advent of partial differential equations and the models of fluids that came out of course, Navier, Stokes, D'Alembert, and Leonard Euler himself in St. Petersburg, Russia. He indeed was a mathematician, a physicist, a philosopher, and a music theorist. He was active in the salons of France. In fact, he had an apartment in the Louvre. And if you're in the Louvre today and you're keen, you can actually find the exact rooms where he lived, which now house famous French paintings. He also created the famous D'Alembert solution to the wave equation, which is one of the three fundamental partial differential equations that we study even today. And I hope that you see this solution in your studies. He has an interesting history in that his mother left him on the steps of the Saint Jean-Laurent de Paris church, which of course you can see the site of it today. And he's named after the patron saint of the church. His education was secretly paid for by his father, who was royalty. Of course, he was born out of wedlock to a mother who was not a royal, and therefore his, of course, royal status as a son out of wedlock could never ever be known. But his father was a benevolent benefactor and paid for his education. Indeed, in 1740, he published the Memoir sur la fraction de la courbe solides, and theoretically explained the idea of refraction, which occurs in optics and acoustics and electromagnetics. He also, in 1752, as you learned in your previous classes, created and proposed the D'Alembert paradox, meaning that the drag on a body immersed in an inviscid incompressible fluid is zero, which is very troubling. Indeed, as I mentioned, he participated in many salons in Paris. In fact, he was a well-known and outspoken unbeliever, which is what they called atheists at the time. And the atheistic term was so offensive to many people between the Protestants and Catholics that they wouldn't even let him be buried in either one's graveyard. The Catholics would be buried in the Catholic graveyard, the Protestants in the Protestants' graveyard, and the unbelievers were thrown in a ditch. In his case, he was thrown his lifeless body in an unmarked grave. And this is the most tragic end to the beautiful story of D'Alembert. On the right is, of course, his oil painting. And I'm sure you can understand what a revolutionary mind and genius and an unsung hero of our mathematical theories are today, as all mathematical models are written in his language of partial differential equations. Let's now go on and look at wave drag more. Remember, for supersonic flows, the drag will be finite in the context of the traditional theories of course, in viscid flow. We have discounted viscosity in our, of course, flows, but we have relaxed the incompressible assumption and retained compressibility. Therefore, we do find drag, unlike the D'Alembert paradox, which made the assumption of incompressible flow. Indeed, even if our flow is very, very high speed and we forced it to be incompressible, which is unphysical, we would also find zero drag. And so the drag in the inviscid flow is due to the compressibility effects. This is called the wave drag. You can see how it's connected now. Now remember, the wave drag will be dependent on the total pressure and increase of entropy across the oblique shock waves mainly. You can see it's really the integration of the static pressure. But of course, we can see that the wave drag goes as total pressure and entropy increase, which is the losses in the flow. Let's look at one particular example. Instead of a diamond airfoil, let's look at a flat plate airfoil at a 5-degree angle of attack in a supersonic ambient global Mach number flow of 2.60. We're asked to find the coefficient of lift and coefficient of drag analytically. And so the very dark black line represents our very, very thin aerodynamic body. In fact, it has a infinitely thin thickness. So T is essentially 0, but it does separate the fluid. You can think of it as like a baffle in terms of computational fluid dynamics. The flow moves in horizontally from left to right, and there's an incoming Mach number M1, which is 2.6. The angle of attack is 5 degrees positive, and so the angle of the flow relative to the chord of the flat plate in this case is of course 5 degrees. The flow moves from left to right from 1 to 2. Of course, the flow is deflected downward out of itself, and therefore an expansion wave occurs at the top of the airfoil. Then the flow is once again deflected from 2 to 4, and an oblique shock wave forms. From 1 to 3, a shock wave must form because the flow is deflected by 5 degrees into itself, and here's the shock wave pictured. And then an expansion wave forms because, of course, the flow wraps around the vehicle and reaccelerates. Now, what happens between 4 and 5? Indeed, in this particular case, the static pressures are equal, and this is why an oblique shock wave forms and an expansion wave forms with equal velocity vectors. And you'll notice that after the trailing edge in the wake of this flat plate, we indeed have a non-zero angle in degrees, capital Phi. So the velocity of the flow does not return to the parallel direction. This is because we have the requirement that the static pressure in 4 and 5 be equal. If the flow returned to the horizontal incoming direction relative to the original flow in 1, the velocity vectors would be parallel before and after the vehicle, then of course we could not hold the condition of static pressures be equal, which is a requirement given the assumptions we made of compressibility and of course in viscid flow. So the question is, how do we find CL and CD from this case? Let's try that now. We'll first seek the solution in region 2. Let's try that now. You'll see in region 2, from 1 to 2, we know flow in 1. We'll have to find, through a Prandtl-Meyer expansion, a table lookup at Mach 2.6. You'll find the appropriate Prandtl-Meyer function of 41.41 degrees. We have a flow deflection angle of 5 degrees. We use theta, the turning angle goes as the difference of the Prandtl-Meyer functions. So theta 2 will be, of course, Prandtl-Meyer function at Mach 2 minus the Prandtl-Meyer function at Mach 1 in region 1. Therefore, we know theta and we know nu m1. We can solve for nu m2. Let's do that now in the next line. We'll say nu m2 equals nu m1 plus the angle of attack, which is theta in this case. That happens to be 41.41 degrees, which is the Prandtl-Meyer function at 41.1 degrees, plus the 5-degree turning angle. And of course, we get 46.41 degrees. Now, we go back in our tables or solve the Prandtl-Meyer equation for 46.41 degrees, and you'll find in a corresponding row or evaluation of the table or equation, you'll find M2, the Mach number in region 2 is 2.85 degrees. Notice we went from Mach 2.6 in region 1 to indeed Mach 2, 2.85 in region 2. Okay, well that's great. Now, from the isentropic table for Mach 1 to 2.6, we have a total pressure over a static pressure of 19.95. And now, in region 2, we went to a Mach number 2.85, which makes sense because the expansion wave increased the Mach number of the flow. It didn't decrease it like a shock wave. We can then look and find that PO2 over P2 at M2 is 29.29. Indeed, PO1 equals PO2 because, as we showed in the previous class, the isentropic flow occurs through the expansion. Therefore, we know PO1 equals PO2, and therefore we can solve for P2 over P1 by taking the ratio, as I did in 549. You can see P2 over P1 goes as, expanding out, P2 over P1 times PO2 over PO2 times PO1 over PO1. Rearranging as P2 over PO2 times PO2 over PO1 times PO1 over P1 will go as 1 over 29.29, which we found here, times 1, because PO2 over PO1 are equal, times 19.95, which we found at Mach 1 2.6 as 19.95. Doing the mathematics, you'll find that we get a ratio P2 over P1 is 0.681. Okay, so we have found the pressure ratio on the top side of the vehicle. We now need to find the solution in region 3, which of course is the pressure side of the vehicle through the oblique shock from 1 to 3. Let's try that now. You'll see from our theta beta Mach number diagram, for an incoming Mach number 2.6, that's the family of solutions. For a turning angle of 5 degrees, you'll find a wave angle of 26.5 degrees. We then find the normal Mach number to cross the shock. Remember, through trigonometry, the normal Mach number to the shock between 1 and 3 is the incoming Mach number times the sine of the wave angle. We can fill those in. M1 is 2.6 with a wave angle beta of 26.5 degrees. Evaluating this, you'll get 1.16. Therefore, Mn1 is 1.16. We then can use the normal shock equations or the normal shock table and look up Mn1 of 1.16. Look over for the column for P3 over P1, and you'll directly find 1.403. So the static pressure ratio across the oblique shock between 1 and 3 on the pressure side of the airfoil has the ratio of course, 1.403, which you can see makes sense because the static pressure is rising. So now we have the static pressure ratios above and below the airfoil through the expansion and shock wave, respectively. We can now seek particular coefficients for lift and drag. Let's define our lift coefficient this way as L prime and our drag coefficients as D prime. Lift will go as P3 minus P2, that's the pressure difference across the plate, times its chord times cosine alpha, which is of course the projection of the chord with respect to the angle of attack of the pressure forcing in the cross-stream direction. And that's per unit span, so we have a unit span. The drag will be the same equation, but with a sign to project the pressure forces in the axial or streamwise direction of flow, sine alpha. So it's the same equation. We'll now define our dynamic pressure in the classic compressible flow sense, and it might be a good exercise for you to show indeed that gamma over 2 P1 M1 squared goes as, of course, the dynamic pressure in the traditional sense. We'll write that as Q. Perhaps you've heard of max Q during the launch of particular aerospace vehicles, like rockets. Let's fill in our equations now and define coefficient of lift as the lift divided by the dynamic pressure times the chord. And indeed, we've defined a non-dimensional quantity. We can then fill in these parameters, and we'll get 2 over gamma M1 squared times P3 over P1 minus P2 over P1 times cosine alpha. Indeed, putting in the numbers, because we know these ratios now, we'll have these numbers here, which after plugging and chugging, if you will, you'll get 0.152. So indeed, our coefficient of lift for this particular situation for the wave drag and wave lift is 0.152. If we had an angle of attack of 0, of course, our coefficient of lift would be 0. Next, you can also find the coefficient of drag. The coefficient of drag is d prime over q1c, which, filling in, will be 2 over gamma m1 squared times p3 over p1 minus p2 over p1 times sine alpha. Notice that's exactly like equation 552, but of course we have a sine alpha now. Imagine alpha going into 0, and of course sine alpha goes to 0, and once again you have 0 drag, which makes sense, of course, because of the theory of the wave drag. Indeed, at real zero angle of attack, you will have a real drag because, of course, there's a body and it has a no-slip condition causing shocks to form. We're just not considering that case in the present theory, where we have assumed inviscid slip conditions on the airfoil. We would have to assume no slip to properly do the problem for, of course, the case for shallow angle of attack, like a equals 0. Let's plug in the numbers now, of course, with sine 5, just like before, instead of cosine 5, and you'll get a coefficient of drag of 0.0133. This is very typical for a coefficient of drag to be much lower than coefficient of lift, and you would indeed know in the joke that aerodynamicists who try and reduce drag would do anything to reduce the count of the drag, which you see here on the right-hand side of 555. Now, let's make some interesting notes on the problem we just analyzed. You'll notice that the entropy in region 4 is indeed different in the region of entropy 5 in the wake of the vehicle, as I mentioned before. So after the flow turns to the final shock and expansion at the trailing edge, we will have a different direction. And this is, of course, due to a particular difference in pressure, which must equalize, which causes the flow to divert. This pressure, indeed, is the same in region 4 and 5, because, of course, we need parallel streamlines in the theory we developed. And we generally see this in reality. Now, the velocities have different magnitudes, but in the same directions, and of course, this creates a slip line. And this will cause theta to be, of course, formed, which is the flow deflection angle relative to the vehicle. This means that the flow for positive alpha is typically turned up. And in this particular calculation, phi is roughly a value of 10 degrees. You should find it to be an exercise yourself to find that flow deflection angle phi through an iterative approach. We might ask, does this generate lift? Does it generate additional aerodynamic forces which we must account for on the vehicle? And of course, generally the answer is yes. Let's return and apply now this new theory of the shocks and expansion theory to the beautiful problem of the diamond airfoil and do some thought experiments. You can follow along this mathematical and physical reasoning in the paper by Mauchel, W.E., and Theoretical Aerodynamic Coefficients of Two-Dimensional Supersonic Biplanes, which was published in NACA, that is NACA, Technical Note 1316 in 1947. Up here we have the typical diamond airfoil. As you can see, it has a total angle of theta and half angle of theta over 2. It has some chord, which he calls A, and this has a thickness D, and there's some angle of attack alpha. Now imagine we simply cut this in half in the streamwise direction and form this shape in part B. We might call this a so-called biplane. And of course, biplanes were very popular. And why not think about a biplane with the construction and cut through the chord of a diamond airfoil? We would take the bottom triangle and place it on the top, and the top triangle and place it on the bottom. And we'd separate them by a distance d. Now this looks very much like the converging diverging ducts, which we developed for nozzles, inlets, and double converging diverging ducts for wind tunnels. You can see now we're starting to take the airfoil problem and transform it into the traditional problems we studied earlier for shock and expansion theory. It's a work of a keen transformation. Here there's the basic nomenclature, which I'll read through you can read through to understand all the nomenclature. I'll talk about the big picture, and you can focus on the nomenclature details. Now let's say we take B, the so-called biplane with triangular sections, and perform the same shock expansion theory for the whole flow that we did earlier for the interior of the flow. And we have some small positive angle of attack. Over the top of the vehicle, we of course have an expansion as the flow turns out of itself. And under the bottom of the vehicle, the pressure side of the vehicle, towards the ground, will have a shock wave as the flow is deflected into itself by angle alpha. But what happens to the interior of the vehicle? It is very much like the supersonic inlet problem, exactly like we studied before. In fact, shock waves form on the top and bottom of the vehicle triangular airfoil elements and merge into a reflected oblique shock. If we have an appropriate incoming Mach number and position these triangles exactly at the correct locations, these shock waves will reflect and exactly hit the tips of the triangles above. It's not required, it's just we have positioned the triangles and the angle of attack and Mach number to exactly get this case. Like we talked about in the reflecting shock wave case, for certain wall turning angles, they will either reflect as a shock, nothing, or an expansion. In this case, you can see the flow after the shock wave indeed must be turned and be parallel to the wall, and therefore an expansion wave forms at the tip where the shock wave hits the wall. And therefore, in this case, if we turn the wall out of itself relative to the flow, if you will, in slang, we can form these expansion waves. Take a few minutes and try and understand the physics of this. Now, along the straight walls, the expansion waves will come along and bounce off the walls as additional expansion waves. Indeed, the expansion waves create that cross net, which we can analyze with method of characteristics, which we'll learn later in this class. You can see in this particular case, this acts as indeed a compressor, which is the inlet and convergence section, and the divergence section, a kind of nozzle where the flow is expanding. And so we've taken the diamond airfoil, cut it in two, and created a converging divergent nozzle. And indeed, if we put fuel in the middle and burnt it, we would indeed have an engine with no moving parts that consists of a compressor from the shock waves and a nozzle from the expansion waves and heat and pressure addition from a combustion process with no moving parts. It's a genius idea and analogy. Let's look at more complicated examples. Here's another particular angle of attack and positions of the plates. In this case, we have the same fronts. Of course, this is the full analysis. And through, of course, our Prandtl-Meyer theory, you can see indeed, if we march downstream from cell to cell where the expansions cross, we can calculate every angle of degrees of each of the waves and, of course, marching downstream, their new properties simply by looking up each particular Prandtl-Meyer expansion function and corresponding flow turning angle from states like, marching downstream from one state to another. And that's how, of course, these types of problems are done in practice. And so this particular author, Dr. Malkal, has completely analyzed the supersonic biplane problem using shock and expansion theory. Of course, if we put this device in the wind tunnel, we'll actually have rather good results relative to the present theory. Because remember, the flow dynamics are dominated by the shocks and expansions in the flow for, of course, moderate supersonic speeds. Here's one graph of both experiment and theoretical biplanes. Now, this line here, the dashed dot line, represents the diamond airfoil. The black line is the thin flat plate. And, of course, the biplane, which we just looked at an angle of 7 degrees, is the solid line here. Now, you'll see on the x-axis, we have angle of attack, and the y-axis has the lift-drag ratio, which we just derived for any of these problems, CL over CD. You could easily find CL and CD for the diamond airfoil and the biplane using the exact same theory, and that's what he did in his publication in 1947 to plot these results. And of course, for particular angles, he's particular angles of the vehicle, he's shown these on here on the graphs. Now you'll see, of course, the diamond airfoil is this dashed line or this dashed line, which goes to 0. The thin flat plate, is the dashed long line here, which goes up asymptotically. And of course, you can see for the diamond airfoil, the biplane, you actually get excellent performance. In fact, the peak performance at an angle of attack about 1.5 degrees with a lift-drag ratio, coefficient lift, coefficient drag ratio of about maybe 14 or 15. And that's excellent. And so you can see, might be able to construct this supersonic biplane to achieve really optimal lift and drag ratios, which is always good at very small angles of attack. Now let's try and do a thought experiment and take the lower triangle from the diamond airfoil split and flip it over on its x-axis and make it smaller and move it forward. This is what's shown in the report by Malkal. You'll see it now has a length L, and the upper triangle has a longer length C. It's again at a small angle of attack. Here we have a leading oblique shock which bounces off the lower part of the cowl, if you will, and returns and creates an expansion. This is an optimal configuration. Now look how we have a large body, and off the body we have a smaller body. Now imagine I extend this out and make it three-dimensional and flip it upside down. Here is the inspiration for this particular hypersonics test. Here's, if you imagine, the previous figure is now flipped upside down, the major part of the vehicle. And then here, up here, is the lower triangle. So the flow moves from lower right to upper left in the wind tunnel, and it turns through turning angles, and an oblique shock forms, and it moves along and it hits the cowl. And it bounces around the shock waves inside the duct, and then the duct expands again, creating expansions. They inject fuel in here and, of course, burn it through combustion, raising the total pressure and temperature, and the remaining part of the flow, even outside the nozzle here, is designed to reaccelerate the flow and create thrust. Indeed, this is a hypersonic test at Mach 7 of a full-scale model from NASA Langley's 8-foot high-temperature tunnel. You can read more about this particular test at this following web address for the so-called X-43A hypersonic test vehicle. The X-43A was, of course, an X-plane, which is a test vehicle developed by NASA to understand high-speed combustion hypersonic tests with no moving parts based on the beautiful theories of shock expansions. Here's a more realistic diagram, which is very much like in Figure 316, Figure 12 from 1947 of the general theory. You can see now this is a basic outline of how this propulsion airframe integration works. The flow moves left to right, and it's compressed by a series of shock waves inside the duct and outside, and then fuel is injected in this region where the flow becomes very slow but remains supersonic, and then it's expanded out the nozzle. That's exactly like the full-scale vehicle test in the wind tunnel and, of course, in the atmosphere. You can read about this on your own to understand these concepts in greater detail if you so desire. But just understand, the idea of shock expansion theory came from the idea of a simple flat plate, then diamond airfoil, out of the ideas, of course, of D. Allen Bay and Theodore Meyer, and were extended to the airfoil problem and then split in two, which became the original ideas and concepts of this advanced propulsion system for hypersonics. Let's now change our attention to the idea of downwash. Downwash is pictured graphically here. If we have a very high angle of attack and a very high Mach number on, say, a flat plate or any type of flight vehicle, strong expansions will occur on top of the vehicle and strong shocks will happen at the bottom. At the end of the vehicle, we'll have an upward moving shock wave and a lower moving expansion wave. Indeed, in both cases, the expansion wave is very strong and it merges with the trailing shock. In the lower case, the expansion wave is very strong from the trailing edge of the vehicle and it merges with the leading shock. In both cases, the waves are so strong that when they coalesce together, they either turn the wave to a higher wave angle with respect to the flow or turn the wave in a shallower angle with respect to the flow, as shown in the lower part of the image. This phenomena is called downwash. We're not handling the physics and math of this in the class. I think you can actually understand the physics now that you understand coalescence and the of particular waves, in this case of shock waves and expansion waves. It'll change the properties at the wave front and change the wave angle. You can see this happens in reality at high-speed vehicles, which you can visualize, of course, in flight. Let's look at the last major subject of this class, which of course is the idea of expansion angles of very large angle. So far, when we evaluated the Prandtl-Meyer expansions, we considered relatively small angles. But how large of an angle can we really have mathematically? Well, we can take the Prandtl-Meyer expansion and let, of course, the Mach number after the expansion or go to infinity and see what happens to the turning angle, which is, of course, the angle which the flow is turned. So you see here in the thought problem, we have a Mach number and flow going from left to right at Mach 1. To obtain the maximum expansion angle, of course, we want the flow to beat the transonic condition. So we can have a maximum angle turning according to theta as Prandtl-Meyer function 2 minus Prandtl-Meyer function state 1. So the flow moves along and the flow can be turned and the streamlines will wrap around the surface and go towards M2 as it goes to infinity. And you can see here, I've already let the cat out of the bag, so to speak, and you'll find a maximum turning angle of 130.45 degrees. Let's do the mathematical analysis through the limit. In equation 556 of the slide deck, I have shown the Prandtl-Meyer function, which we derived in the previous classes. It's, of course, nu of Mach number goes as the square root of gamma plus 1 over gamma minus 1 times the arctan, of course, of square root of gamma minus 1 over gamma plus 1, m squared minus 1 minus arctan of square root of m squared minus 1. That's also in your equation sheet and tabulated in your tables. Now we'll take the limit as Mach number goes to infinity. Perform the operation, you'll find a slight reduction as m goes to infinity, and you'll find gamma plus 1 over gamma minus 1 to the half times times pi over 2 minus pi over 2. Evaluating that term and putting in terms of degrees, you'll find 130.45 degrees, which is shown in the figure 2. So that means if we let our Mach number go to infinity over an expansion of about 130.454 degrees, at gamma 1.4, you'll have a different angle for different degrees. Then you're, of course, will have a maximum turning angle of your expansion. Now, we can then evaluate the pressure and temperature in state 2 given this particular Mach expansion according to isentropic theory to go from 1 to 2. But you'll find, of course, that the pressure and temperature will go down to 0, which is just not possible in expansion. In fact, what will happen in physical reality, if you have a large expansion as light like this, is that the flow will simply just go off the end of the surface and separate. It's very unlikely that, of course, you'll have this nice attached flow over a large angle. But indeed, the pressure gradient is indeed in your favor. And therefore, it's very much likely that the flow wants to be attached. And so, through Prandtl-Meyer expansions, you can have rather aggressive angles and keep the flow attached for many situations where you would think it would not occur otherwise. In this class, we introduced the idea of shock expansion theory, which is nothing less than combining the ideas of oblique shock waves with Prandtl-Meyer expansion theory. We then applied that directly to the most classic problem of the diamond airfoil. We then looked at an example of a flat plate airfoil, and then looked at the particular wave drag, which is the integration of static pressure over the airfoil. Remember, wave lift and drag are the dominant forces at moderate supersonic speeds for these problems. We then derived and looked at particular emphasis in historical context of finding supersonic ram jets, which we illustrated through the X-43 experiment, which is nothing but the diamond airfoil cut in two according to shock expansion theory with fuel injection and no moving parts. Indeed, this is one of the engines of the present and will dominate the future. We also looked at the asymptotic analysis, of course, the expansion theory very briefly, and I encourage you to repeat that analysis on your own. Thank you very much for your time today. I'm Professor Steve Miller.